So I have a list of people who have been contributing to the working group over here. I'm sure I missed a few names. Apologies in advance if I missed your name. There is a bunch of documents on the wiki page which you can look at for the progress of the working group. We meet once every 2 weeks, and of course, people are welcome to join and help us define this as well. So I will give a somewhat of a high-level overview of the plans that we are doing for the UCD initially, and to the later part of these slides, I'll get into more technical details of what exactly is going on. I only have like 20 slides for an hour, so please ask me a lot of questions. There needs to be enough questions to fill out the 60 minutes, otherwise Pasha is not going to be very happy. Okay, so let me see. Okay, all right. So a lot of or most of the work for the UCD working group is to deal with non-contiguous data movement, although that's not the only piece that we have been looking at. It's very important for both scientific computing, for example, with API, as well as for modern deep learning systems. We have several vendors working on deep learning systems. Some are public, like Facebook and so on. Some are still in startup mode, but they are all using UCX today for doing their data movement. But they have needs for non-contiguous movements of data, mostly in the forms of multi-dimensional arrays, though that is not always the case, but most times it's in multi-dimensional arrays, where they want to move between different processes through UCX. And the intent of this effort is to allow the users to create or specify static non-contiguous data layouts and provide that information to UCX so that UCX can move the data more efficiently than what the user can do. UCX today has a few options for moving data. Of course, there is the contiguous data movement option where it essentially treats the buffer as a bunch of bytes and moves the data across a wire. That option exists. There's a second option called Iov, where the UCX allows the users to describe data as a series of contiguous chunks. So you give an array of base pointers and lengths, and each of them is contiguous, so UCX can move them through an Iov. There's a third mode called generic. This model is where the user passes no information about the data layout to UCX. So user essentially says that here is a buffer and gives pointers for pack and pack, and UCX doesn't know anything about the data layout, so it will have to ask the user to pack the data or unpack the data. So, the code has a fourth mode called strided, but as far as I could tell, there is no implementation for that yet. But someone should correct me if I'm wrong on that. So here's a picture on the right-hand side over here. This is the three-dimensional block of three-dimensional array, and users might move. So we have X, Y, and Z axes over here. X is the leading dimension. This is, let's say, C-style programming. So X is the leading dimension. The next dimension is Y, and the third is Z. So if you want to move either the XZ or YZ planes, you have non-contiguous data that needs to be moved. So these sort of problems is what UCD is trying to address. So what are we missing in UCX? So there are a few things that are hard or impossible to do in UCX. First is if you want to look at things like reductions, which is important for collectives, but also for RNA accumulates, it is impossible to do that with UCX right now unless you specify what the base type is. It's integer or float, double, whatever it is. Right now, UCX just treats it as a bunch of bytes, and we can't do arithmetic operations on these series of bytes. We need to convert them to some basic language level data types. It's possible, but inefficient to utilize hardware features such as UMR. In theory, one can pass an Iov to UCX, and UCX can go and analyze the Iov to figure out that this is actually an vector style format, so I can do a InfiniBand UMR. But it's very inefficient to do that because creating the Iov as well as parsing the Iov can be very expensive. And third, it's kind of hard to decide between when I should use the IOV model versus the generic pack and pack model. So if you look at the picture over here, the YZ dimension on the right-hand side, this is essentially, let's say each of these elements is a double. Each of these is contiguous at a double granularity. So packing, usually generic model, is typically better to send data to your left and right. But if you want to send to your top and bottom neighbors, depending on the length of your X dimension, IOV might be better. And when I say depending on the length of the X dimension, it depends very much on the network hardware that is used. For some networks, a small X dimension is good enough. For other networks, a very large X is needed before IOV is useful. So it can get a little messy if the user has to figure this out. Instead, if UCX can handle this, that's better. And the next point is it's inconvenient, possible, but inconvenient to move non-contiguous data from non-CPU memory. So this is one of the problems we are running in with MPICH as well, where when we want to use a generic type, the temporary buffer that UCX provides to MPICH resides on the host. I know that Devendra and Akshay and others are working on alternate implementation where the temporary buffers can be on a specific GPU device. But for now, the temporary buffer is always on the CPU. So we always pack from in the MPICH code, we always pack user GPU data to the host buffer, and the host buffer will then need to transfer it host to host and unpack it again on the GPU. So we are kind of losing all the benefits of GDR copy, for example. A quick note about some shortcomings of the IOV-based data type processing. Right now, this is the only way where we can pass non-contiguous data information to UCX, apart from Strider, which I believe is not implemented. So in this IOV-based model, I want to point out that in theory, we can pass non-contiguous data type information to UCX with IOV, but it might not be very efficient in practice. Sorry, I can't hear you. Go ahead. Was there a question?
No, just somebody forgot to mute. I muted. Don't worry.
All right. Okay, so so for the IOV thing, while it's theoretically possible, it's very inefficient for some sorts of data layouts. So in this particular example, for example, if you want to just send one element each in each of the Z dimension, creating IOV is actually much more expensive than just packing the data, because the IOV, you have to load a base pointer and an address, which is actually more bytes than the data itself. So it can get very expensive. So while it is possible, it might not be the best solution in many cases. All right, so that's where UCD comes in. It's a non-contiguous data engine. I should call it predefined and non-contiguous data type engine. So it provides almost all of the MPI data type functionality with some additions that we felt are needed beyond what MPI gives. There are 4 sets of APIs that it provides. The first is predefined data types and the data type creation APIs. So all basic data types are provided. We can look at that in a bit. The second set is pack, unpack, and accumulate sort of routines, where the user can give a non-contiguous buffer and either pack that or pack with an operation like a sum it up onto another buffer. There are IOV routines, of course, for cases where it's non-contiguous, but each contiguous piece is large enough. And the fourth one is called a flatten, unflatten routine. This is mostly for one-sided communication. I will talk a little bit more about that in the later slides. I should point out that all of this UCD, we're working on a code, and almost all of the code for UCD is essentially a wrapper for another software library called Yaksa. So it internally utilizes that, essentially wraps around Yaksa to provide UCX-like functionality to users. And Yaksa itself, I have more slides on Yaksa itself in a bit, but it is, we have full functionality for of course, for CPUs, but also for NVIDIA GPUs and Intel GPUs. The AMD GPU support is not complete yet. We are still working on that part. Okay, so the data type creation routine. So first of all, there are a bunch of predefined data types. In fact, it has predefined data types for all C99 data types, which are listed on, some examples are listed over here: integer, float, double, and so on. But you can also create non-contiguous data types, such as vector, for example. Here's a quick API for that. And this is a hierarchical construction. So you can create more data types out of the previously created data types. You start with the basic data type, like a double or something, and you keep building on top of that, like a vector or a vector of vector, something like that. And it has all of the functionality of MPI plus more. So you could easily implement all of the MPI functionality. The reason we added more functionality was because of our deep learning customers who have been asking for some things that are not a part of MPI. One small thing I do want to point out, but it's on our roadmap, is we do not have basic data type support for things like bfloat and so on. But that's on the roadmap. We'll probably add those going forward. The second set is a pack unpack routines. So these are non-blocking pack unpack routines. So you can take a non-contiguous buffer and a data type associated with that, and pack it into a temporary or some output buffer. These are extended versions of MPI pack unpack. So you can give an offset of where to start, and you can also do partial packing. So it allows for pipelining. For example, if you have only a temporary buffer of 64 kilobytes or a megabyte or whatever, you can pack some part of the data into this temporary buffer, send it out, pack the next part of the buffer, and so on. So it allows, it's better, it has more options that allow for better integration with MPI or UCX or things like that. The reason for the non-blocking packing is mostly for GPU resident buffers. So when you have a buffer residing on the GPU, you want to initiate the pack, but you might not want to wait for it to complete. So you can do a non-blocking pack and do something else and come back and see it as completed. We have support for a bunch of predefined operations. So we have things like summation, bitwise OR, logical OR, product, and various other forms. Not all of these operations might be supported by the network hardware, but for cases where it's not supported, some software emulation is possible. Next is the Iov routines. Like I said, in some cases, IOVs might be better than packing data. For example, if each contiguous chunk in your non-contiguous data, if each contiguous chunk is very large, you probably don't want to pack it. Instead, you want to send each of these contiguous chunks individually. So here's an example over here. So you check the IOV length of your data type. You get the average average length of the contiguous chunks. If that average length is more than some threshold, you would convert it to an IOV and issue each IOV operation separately. If it is less than the threshold, you will pack the data and then do a single send for all of the packed data. So something like that is the intended usage. So we expect users to use some combination of IOV communication as well as pack and pack communication, depending on some threshold. Now here, the quote unquote, the user of this would be something like UCP or UCC, not the end user. So we expect that the end user to simply say, here is a data type and send it out for me. And UCP or UCC will have some internal threshold to figure out when to do IOV-based communication versus pack and pack-based communication. Now, finally, the flatten, unflatten routines. Flatten, unflatten, these mostly are for, like I said, for one-sided communication. The intent is that in some cases, the remote process might not have information of the data type because the origin process might be providing both the origin side data type and the target side data type. In those cases, we have these routines called flatten and unflatten, which will convert a UCD data type into a portable format, which can be transferred across processes. So you convert it to this portable format, you send it out to the target process, and the target process would unflatten it to recreate the data type and receive the data. This is mostly for active message sort of models. If you're doing RDMA sort of communication, you don't need, I should say, if you're doing RDMA put sort of communication, you don't need the flatten unflatten. If you need RDMA get sort of communication, then you probably still need this flatten unflatten. A few general comments. I should point out that all routines in the UCD API are local, which means that everything will complete immediately in a finite amount of time. Now it is a valid implementation for all, for example, an IPAC call to block till the pack is complete. Although it's probably not the best implementation to do that. So for the way we do it is for the sequential code, we probably do it as a blocking call on the CPU, but for GPU-based communication, we make it as non-blocking calls. That's the general overview of UCD. I want to point out one more thing. The working group has already pointed out several concerns, changes that are needed for this API. I apologize, I didn't incorporate those in the slides or in the code yet, but the intent here is not to ignore those comments, but it's just that I didn't get time to incorporate those yet. But this is roughly speaking, that's the idea of how these APIs are going to look like. Okay. All right, I'll keep going. If there are any questions, please feel free to interrupt me. Otherwise, I'll keep moving forward. Like I said earlier, UCD is mostly just a wrapper engine. Internally, it uses an external software called Yaxa to do the actual processing of the data. I'll talk a little bit about the Yaxa engine itself to talk about what kind of features it supports. But this is mostly hidden from UCX. UCD wraps around it to give whatever functionality UCX needs from it. The Yaxa software architecture itself is a multi-layer architecture. There is a front end, which does basically device-independent pieces, handles various corner cases. I'll talk about that in a bit. There's a backend glue layer, which manages inter-driver interactions. I'll talk about that as well. And at the bottommost layer, we have a bunch of backend drivers that are there. We have a sequential driver. This is mostly for the CPU systems, where we do a multi-level for loop for doing the packing and packing and so on. We have a CUDA driver, which is also fully implemented and supported. There are some performance optimizations that we need to look at, but it's basically fully implemented. There is a ZE driver. ZE is the Intel GPU API, one API, the level 0 API. So there is a full implementation for that, for pack and pack IOV and so on. The only piece, I put a work in progress over there. The only piece that is work in progress is the reduction operations. Those are implemented, but there are several bugs in those. So the Intel folks are working hard on fixing that. So I put a work in progress over there, but it should be, the reduction part should be ready fairly soon. The non-reduction part is already functional for the Intel GPUs. The AMD GPU stuff is not done yet. The primary reason for that is the Yaxa was actually motivated, of course, through MPI, but also heavily motivated by our deep learning users. And they are, well, at this point, they're not yet using AMD GPUs. So the priority for us was somewhat lower. But of course, we have several large machines coming up with AMD GPUs, so we're going to increase the priority for that and implement that as well. I should point out that Cray is working on implementing a version of that for AMD GPUs, but it's unlikely that they would open source that part. I don't know yet, but I think it's unlikely they'll open source that part. So we'll have to go ahead and implement it ourselves for AMD GPUs. Maybe we can get some help from the AMD folks with that piece. The backend code generation, I should point out that the way this layering of the XI is structured is that the front end mostly manages a lot of these corner cases for the user provides, like non-zero offsets and partial packing and so on. So the backend itself sees well laid out data structures for packing and packing. So quick animation over here. So if the user wants to send a pack this set of like these red boxes in this picture over here, the front end would split it out into these 3 smaller pack routines, where each of the pack routines is a more well-structured block of nestings that the backend can do. So it kind of makes it convenient to write the backend data structures. And in the common case, we don't expect the first and the last block to be too large. In the common case, we expect the middle block to be large, so the performance is usually very, very good for most applications. I should also point out that on the back end, we generate a lot of nested loops for the packing and packing reduction sort of kernels, nested loops for the sequential code, and parallel kernels for the GPU code. So essentially, they are generated at build time. So it kind of creates this options for saying that, hey, this type, I already have a kernel that is specific to this data type. So I can go and directly call that kernel, which can do an efficient pack for that particular data type. So a quick code snippet for you to take a look at how this code looks like. So it's basically, you can see it's a multi-level for loop that is created. This intent over here, let me just talk a few things over here. It allows for 3-level data types. So it can create, well, this example is only H vector of H vector double, but we can create up to 3 levels. So H vector of H vector of block indexed of double, something like that. So it creates multi-level data types, so suitable up to 4D data structures. So we have not had any requests for more than 4-dimensional data structures. It's still supported more than 4 dimensionals, but you don't have this fast path for larger data types than that. We can use, the kernels are specific to different attribute types that are given a type creation time. For example, the block length is given a type creation time, or the actual data type, like double, is given a type creation time. So we know all this information. So the kernels are very specific to each of the data types, and we generate lots and lots of these kernels to be used. And of course, the core packing and packing loops themselves are very well optimized with restrict pointers, and it tries to make it easy for the compiler to vectorize and prefetch and so on. So it kind of is very efficient for performance reasons. Here's a quick chart with vectorization that happens for the CPU code for Yexa. This is, we did experiments with Clang, GCC, also with the Intel compiler. Most of these experiments were on the x86 platform. I think we're going to try out with the ARM platform as well. So Pasha, we're going to get in touch with you to kind of help out with that. But we get very good vectorization results. It depends on the kind of data type you have. If you use like something like a vector data types at the bottommost layer, we get almost 80% vectorization. Almost 80% of the loops are vectorized in that. But if you use something like block indexed or indexed, the amount of vectorization reduces because you have additional pointer dereferencing that happens. So compilers can't vectorize across pointer dereferences. So, but that's expected. We don't expect the vectorization to happen in all cases. That's with the sequential backend. For the GPU backends, like I mentioned, we have 2 GPU backends right now. We have one for CUDA and one for ZE is the Intel GPU backend. And we have the AMD GPU backend in progress that's going on. And these GPU backends are not based on tight for loops. They're rather based on parallel kernels offloads for doing these packing and packing. We maintain multiple temporary buffers for all of this work. We have some buffers for staging data, for example, like moving data from device to host and so on. And we have some buffers for data type metadata itself, because the GPU needs to know the layout of the data. So we maintain some temporary buffers for doing that as well. And for the staging data, we use your traditional GPU resident buffers. For data type metadata, we use managed buffers because they are much more efficient for us to create and maintain, because the GPU runtime has the ability to evict data types that are not commonly used. So if an application is using some data types more commonly, the GPU runtime would automatically put those data types on the GPU memory. So it's kind of efficient for us to do it that way. I put an example with CUDA over here. We have a similar example with ZE as well. ZE kernels are basically OpenCL kernels. So it's very similar to the CUDA, let's say the driver API, but it's essentially a different set of code that is generated. This example over here is just for CUDA. So you see that we generate two types, essentially two sets of functions for each type. One is the device piece, the part of the code that is run on the device itself, which essentially just does, each thread basically does a small part of the pack and pack. And then there's a host side on the left-hand side over here, which does the host piece to launch the kernel and so on. Apologies, the CUDA stream synchronize accidentally gotten over here. We don't actually synchronize it on every kernel. It's non-blocking operations. So during our testing, I had added that. Apologize, I forgot to remove that in this over here. But it's very efficiently done, and it's essentially launches a kernel and hands off the event associated with the kernel back to the upper layers. And lastly, the glue layer that sits between the front end and the backend drivers. The glue layer essentially handles multi-driver, or like, for example, CUDA and sequential drivers, or device-to-device interactions of a single driver. Basically, anything that needs temporary buffers is handled by the glue layer. And it keeps a progress engine to keep track of what temporary buffers to use, what thresholds to use, and blah, blah, blah. So it does a lot of this bookkeeping for the driver layers. So the drivers themselves don't have to deal with all of this complexity. It also does a lot of work to convert all zero-copy calls to be put-based rather than get-based. I think we saw in Saurav's call for the AMD GPUs that put-based is much better than get-based. That general philosophy is true for NVIDIA and Intel GPUs as well. So the backend glue layer essentially converts all of these calls to make put-based calls rather than get-based calls and so on for performance reasons. And it creates these sometimes complex graph structures for temporary buffer management. So if you want to, for example, unpack plus compute from one device to another device, and let's say there's no device-to-device IPC available, then it creates this chain of events that need to happen one after the other to take care of the actual data movement. So there is, for example, pack from a device to a temporary buffer, move it to the host, move it to other device, and a lot of other things like that. This is a 4-event chain. The number of events can get as many as 6 or 7. So the glue layer keeps track of all this stuff to manage all these temporary buffers and the chain of events and so on. And of course, each temporary buffer is a limited size. So there is the progress engine does this one chunk at a time or a few chunks at a time to maximize performance. Maximize performance without using up an arbitrary large number of temporary buffers. Okay, let me move on to the performance numbers, quick performance numbers over here. So this is just a quick pack and pack kernels. This is somewhat of an unfair comparison. I put MPitch master in there as a kind of a boilerplate implementation. I put data loop over here. The reason I put it is this is really old MPitch code. the current latest MPEG does not use data loop, internally using Yaxa as well. So UCD and native UCD versus NTSH would essentially get the same performance because they both eventually just call Yaxa calls. So it might not make much of a difference over here in performance, but just to understand how it goes, I kind of put the old MPEG performance number. So it's a little bit unfair comparison, but I think kind of just to make a point over here. And over here we see on the right hand side, I dropped the MPICH line and showed the different performance numbers. You can see that we do a little bit better than hand-tuned code as well. The reason we do a little bit better than hand-tuned code is because, again, I don't know if this is the most fair comparison, but in the Yaxa kernels, we generate type-specific kernels. So I know upfront that there is the block length, like the single each element in the non-contiguous, the leading dimension is just one element of a double, for example. So I can pass that information to the compiler, which can do better optimizations inside Yaxa. In the hand-tuned code, in this particular version of the hand-tuned code, that information was not passed to the kernel. So it kind of lost some performance for the hand-tuned code. But in theory, the hand-tuned code could have done that as well, but it just makes the user code more clumsy to do that. When you have more than 4D matrices, for example, in 5D matrices, only the first 4 dimensions are used Yaxa to parallelize it. The outermost dimension would have to issue individual calls. So that we lose a little bit of performance in that case, but still we do much better than what we were doing earlier. A quick performance number here with respect to, this is with CUDA, host to host versus device to device. This is, I think this is a very expected number. In the CUDA version, one, there is a lot more parallelism that is going on for the packing, but I think more importantly, there is much higher memory bandwidth, and pack and pack kernels are very memory bandwidth limited. So we can get much better performance, mainly because of the memory bandwidth on the device. Okay, code status of UCD. I apologize. I put up a private, personal URL over there for the Yaxa code. The reason is that I just got the legal go-ahead less than 24 hours ago. Late last evening, I got the legal go-ahead to make it public. So now we can talk about it. It's in this private repo over here, but I intend to move it to, I don't know, the UCC org, I think. I don't know. I have to talk to Yossi or someone to figure out where to move the code. But it's there. People can take a look at it. It doesn't have any of the history because our legal team asked me to collapse all the history and essentially make it one code drop. So it's there, but you can take a look at it. You can see over here that the code itself is just a wrapper around Yaxa. So what it essentially does is during initialization time, it DL opens the Yaxa library. And if it's not available, it just ignores it. And if it is available, it will essentially make a function pointer call to the Yaxa library. And if it's not available, it'll just return unsupported. That was what, based on a previous discussion with Yossi and Pasha, this was the preferred model to implement UCD as. The reason for this is when we integrate this into UCX, there is no LDD dependency on the Yaxa library or CUDA or whatever else it is. There's no dependency on that because you're always DL opening the library. So if a vendor compiles it and packages and sends it to a different machine, if I don't have CUDA libraries over there, there is no problem. You just disable Yaxa support in those cases. Okay. A quick note about the next steps for UCD. Right now, UCD is a standalone library, but it's not very useful as a standalone library because if you were to use it as a standalone library, you might as well have used Yaxa. There was no point of having UCD at all. So the intent is to have some interaction with UCP and UCC to make it useful. So UCD would The intent is that UCD would internally keep track of some data type information. For example, special data types, like it can keep track of information that this particular type, this particular data type is a vector of double with these strides, for example. And UCP or UCC can use that information for converting that data type to UMR. And for non-special data types, in those cases, then UCP would decide whether I should do IOV or packing, and it can internally make that decision. For UCC or even with UCP accumulate sort of operations, the base type of double or int or whatever, that's important information. So that information will probably be kept by the UCD engine and passed on to UCP or UCC as requested. So the intent is that we'll add a few internal APIs which are not user visible, but they can give this additional information to UCP and UCC as requested. But users will not be aware of this. Users cannot see this particular information. And this would allow UCP and UCC to use hardware features directly, such as UMR. A few other things that the working group is thinking about, but we have not yet made a much progress on that, but we have been discussing these things. One is how does UCD or JAXA internally, right now it creates its own set of streams and temporary buffers for each GPUs, but UCP or UCT would also create temporary buffers. So the question was, can UCP or UCT pass these temporary buffers down to JAXA so that we don't have two sets of temporary buffers that are created. So we are still thinking about it. We don't yet have a full solution, but we have some ideas on how we can go about with that. And the second thing is we are looking at runtime generation of pack and pack kernels. Right now, the kernels are all statically generated at build time. But we are trying to see if we can do something like a runtime generation of kernels. So when a data type is created, we create the kernel at that time, so which makes it more efficient for that specific data type. And also it doesn't take up, the library size doesn't explode too much because we're not creating a lot of unused kernels. This is somewhat easy to do with Intel GPUs, or I should say with OpenCL, but it seems like it might be a little harder to do with NVIDIA or AMD GPUs, although someone from NVIDIA or AMD should correct me if I'm wrong over there. Okay, that's all I have. Thank you. I'm happy to take questions on this.
Hi, Pavan. I have a couple of questions.
Yes, go ahead, sir.
Yeah, so this is very useful. So one thing that I wanted to point out was, so in MPI, there can be a case made for having non-local data type commits so that the data type definition is visible to a communicator instead of just being local. So we have seen that if both the sender and the receiver process knows the layout of each other, they can do more efficient zero copy transfers. So do you think that could be something useful to add to this UCD layer as well?
I think the feature in general is very useful. I don't know if it belongs to the UCD layer. The reason is that UCD engine, UCD layer submodule is a single process. It's an intra-process engine. Okay, so any interaction that needs to happen between processes needs to be handled by either UCP or UCT or UCC or something. Okay, so they can flatten a data type and move it around across different processes, but UCD itself doesn't know anything about multiple processes. Does that make sense?
Yeah. I think that makes sense. So the MPI layer should be taking care of that part.
MPI should take care of that, or maybe UCC can take care of that as well, because it's a collective engine and it could handle that for you.
Yeah. So I had one more question that's like more of a philosophical question. So it seems to me that all the communication libraries kind of eventually turn into MPI. So they have collectives, data types, and similar things. So do you have any comment on that?
Oh, I don't know. So this data type engine has, of course, some capabilities inherited from MPI, but it's, of course, broader than that, but probably not too much. How close it looks to MPI, I don't know. Pasha or Yossi, do you want to answer that?
Well, I can comment that like with UCX, we see it as the optional part library. So it's will be up to application to decide if they want to use that type engine that was optimized for hardware or use MPI built one. Like majority of users today don't really need that type. So there's kind of few exceptions. You mentioned MPI and there's MLAI workloads that need certain types of data types. So I think the difference is like it's kind of optional, completely optional for UCX, it's external library, whereas you get kind of this bundle MPI with everything. What do you think, Pavan? Is that more or less correct?
Yeah, I think that's certainly correct. I think the model for UCX in general is quite different from MPI. The kind of users that UCX supports is different from what MPI supports, and things of that sort. So it's not a bad thing to inherit features that we think are useful, and if you think they are might be useful, but you're not sure, I think the ability to make it optional is also, I think, particularly important. Like I said, we have several users apart from MPI in the deep learning community who have been asking for this. But they, of course, they have all found workarounds for that through Yaksa or other means. But since they are all UCX users, they might end up using this more natively. And if that happens in the future, we can reconsider whether to make it default or to still keep it optional or so on. But it has that flexibility in UCX, which in MPI, that flexibility doesn't exist.
Yeah, I'm definitely not opposed to it. I think it's useful. I think the ability to pick and choose the functionality that you need is useful as well.
Yeah. I for I, yeah, I shouldn't mention. Never mind. Other questions?
I will add another comment on the same questions that introduction of data types and libraries like UCX starts to make more and more sense once we see some sort of hardware acceleration capabilities that we can leverage. And this is another kind of motivation for UCX potentially have these capabilities. If your NIC supports scatter gather, or you have DPU with some sort of data processing capabilities, it starts to make sense to make this an option for generic communication library.
Right. I do want to, so even though we talked a lot about non-contiguous data, I want to make sure that people don't forget that there's also the predefined data types part over here. And we just cannot do reductions without at least the predefined part. So at least that part, I think, is very important to have. Otherwise we cannot have reduction at all. That's just not possible. So let's keep that in mind as well, irrespective of whether we want to have non-contiguous data types or not.
Any more questions for Pavan?
I have 15 minutes more, so I think I can take another 10 questions.
One more question related to the packing and unpacking.
Yeah.
So currently the pack unpack seems to involve a GPU kernel launch. Is that correct?
If it is depends. Internally, we look at how large each contiguous chunk is. If each contiguous chunk is large enough, we just do multiple DMA operations. If every contiguous chunk is very small, then we launch a kernel. And users can tweak what that threshold is.
Yeah, so is there a way to like use a CPU based kernel if we think that launching a GPU kernel would be too much overhead?
Right, you can give a hint to essentially set the threshold to basically infinite. In that case, it will always do, it's not a CPU based kernel, it's just a multiple DMA operations, right? Individual DMA operations.
Yeah.
So you can set that threshold to infinite and convert, or basically it will not launch any kernel, it's just essentially the DMA operation. Having said that, I would strongly suggest not doing that, because individual DMA operations for very small contiguous chunks can be very expensive.
Yeah, agreed.
I guess it depends on how much the GPU is utilized. But in our experiments, it was like 2 or 3 orders of magnitude worse than launching the kernel. So 100 to 1,000 times worse.
No, but let's say I have a list of IOVs. So each individual element is fairly small. And I want to compact them into or flatten them. So maybe like I can do some CPU reads through since we have access to the entire GPU memory. And that should take, I don't know, if each rate takes 1 microsecond, it may be done in.
Maybe I'm not understanding what you mean by CPU read. Are you actually doing DMA calls?
No, so if I just access the elements directly, like I'm reading them from the CPU.
You are accessing GPU resident elements from the CPU?
Yeah, the GPU memory is visible to the CPU. So this is true for ROCm GPUs at least. So the entire address space is visible. So I can just like read the element if I want.
Oh, I didn't know. So on NVIDIA, at least, I think if it's a GPU resident buffer, like CUDA malloc buffer, you can't read it from the CPU. You can do that for managed, like CUDA malloc managed buffers, but not for like GPU, like truly GPU resident buffers.
Yes, so for ROCm GPUs, it's possible because the entire, even if you do heap malloc, which is like equivalent of CUDA malloc, the memory is accessible to the CPU. So that was the context of my question. Like, is there an opportunity to use the CPU-based packing in cases where launching a kernel would be too expensive?
Yeah, there is a way to do that. So there's a hint mechanism. I think I can just go back to that slide over here. Okay, there's a hint mechanism over here, the info parameter over here, where you can pass a bunch of hints. So that includes the thresholds that I mentioned earlier, but also the buffer location, the device, whether it's GPU buffer, which device it sits on, what type of buffer it is, and so on. So in that, if you essentially treat that as a CPU buffer and pass that to UCD, UCD will essentially assume that it will not do any checks. It will assume that it's a CPU buffer and essentially do a sequential pack as if it's a CPU buffer. So you can make it do that too. I actually didn't know this, but accidentally this feature became available.
Sure, yeah, that's what I was looking for. Thanks.
But it is good to know. I didn't know that about the AMD GPUs. It's good to know. How does it do that? Does it do individual PIO operations or something, or does it do like individual DMAs or migrate the page? What does it do?
I'm not actually sure how it's internally done. I can look up some details and share with you.
Okay.
Pavan, I'll also add that it's possible to map in GPU memory onto CPU and have the CPU access even though it's not managed memory. It's just that the performance of reads and writes to that map memory would be slower.
Oh, I see. I didn't know about that either. Thank you, Akshay. I think this is something. This part should be discussed in the working group in more detail. I was just not aware of this capability at all. So current code doesn't utilize any of that in any way. It just launches the kernel. Either does a DNA or launches a kernel. Okay. Other questions?
Seems like we out of questions. Okay.
I have a short question, maybe last minute question. I didn't really get how this is going to be integrated into UCX, because this is just somewhat a wrapper on YAXA, right?
Right. So the intent is that, let me go back to this slide. Sorry, I didn't spend too much time on this part over here. Right now, it's a standalone library, which is not very useful. I agree. Let's see. The intent is that UCD would have some internal API, which would only be visible to UCP and UCC. So the third bullet over here. That's the primary way to interact with UCP and UCC. And this internal API would essentially give information about quote unquote special data types that UCP or UCT or whatever cares about. An example could be a vector of doubles or something like that. So for everything that it is not special data type, UCP would simply treat it as a generic type, but decide between IOV versus PAT, because a UCD data type, even if it cannot do anything special about it, at the very least, it can convert between generic and IOV automatically. That it will always have. But on top of that, it can also have some special cases like vector of double could be a special data type, which you can use VMR or something. So the internal APIs, which are not well defined yet. So unfortunately, I can't. I mean, that's just an intent. There's no API that I can present over here yet. But we are discussing that in the working groups, and we'll hopefully in the next by the next time we'll have a better API to present for both the public API as well as the internal API. Does that help clarify it a little bit?
I think so. So UCX will have to check whether this UCD is available on the system. And if it's not, UCP or UCC will just fall back to the current behavior. Is it the intent?
Well, kind of. UCT itself, in the sense the header itself, might always be available. It's just that it might, in case that I can't do anything useful, it might just return this error not supported. So whenever you try to create a data type, it might return to the user error message.
I see. So that was my question about YAXA dependency. So UCD will manage itself.
Correct. So that's my intent. Again, this thing needs to be polished a little bit. So my understanding here might not be the same as what my discussion with YAXA, with Yossi and Tasha was earlier. So they should correct me if I'm wrong here. But that's my understanding, that the header itself will always be available, but it might return not supported when internally if it can't do something. Is that right?
I see. Thanks. I mean, that answers my question.
Yeah, and there is this, all this is DL open function pointers. So there is no like a link time dependency on YAXA or any of the other libraries that YAXA depends on, like CUDA or level 0 libraries and so on.